All right, so I have a video posted for you guys here. I show it in advanced functions usually. We're not going to rewatch it, but it's just kind of a guy that's explaining the idea of E. So I'll just kind of summarize it for you guys. It just basically talks about when we think about exponential growth, things that grow usually do so over time, okay, gradually over time. And when we think about exponential growth, for instance, maybe I'll just write it down here. For instance, 2 to the x, you guys don't have to write this. But 2 to the x, we use this a lot because it's kind of like the idea of doubling, right? So the guy talks about how if we think about money, doubling our money, for instance, over a year, we have our money, and let's say we invest $1. And he kind of talks about like at the end of that year, if I'm doubling my money, all of a sudden I have a new dollar, right? And it just kind of comes out of nowhere. And then after that, we have the dollar, let's say a year after that, and the dollar that we made from the year before. And then we all of a sudden get 2 new dollars, right? Because it's doubling. Okay, so this isn't quite a nice idea of growth because we get kind of this like staircase type thing where that doesn't really happen in life, right? When we think about even like a plant growing, that plant is going to grow naturally over time, right? And we get this kind of like more natural curve. And the same thing happens with money, right? So as we're gaining interest on something, usually we don't get money that just compounds right at the end of the year. What happens is we get money that actually kind of grows like this, right? So as I have my dollar that's growing here, as I have my dollar that I invested, over time, throughout the year, it's going to kind of have another dollar that's like emerging out of it gradually, right? And then at the end of that year, I have the extra dollar of my doubled money, right? Yeah, there you go, mitosis. So that's kind of the thought. So he talks about when we have continuous growth that's happening like this, right? It slowly emerges and the interest is being added over time. That curve that we actually get is the curve e to the x. And that just represents continuous natural growth. That's the idea of E. So I usually do this with my advanced functions class, so you might remember this from last year. Oh, and I can't erase again. That's good. Okay. So we'll just do this. Okay, so we're going to use this formula. You may recognize this as something close to the compound interest formula. You good? Okay. We are investing $1. I'm going to use that as our kind of just example for this one. And we are going to make 100% of that dollar back, right? So this is 100% of my investment. So 100% of our $1. And we're going to talk about 100% growth. Or in other words, when I talk about 100% growth, I talk about doubling, right? So I am making double what I had the year before, or 100% of that. I'm making it every year. So that is why we have the 1 here. This is 100% interest. And then our n's here are going to represent the number of compounds. And we're just going to look at this annually. So this is just going to be number of compounds in a year. Okay? Normally our n just represents like the total number of compounds over the total number of years, but we're just looking at one single year here, so it's just going to be the total number of compounds we have within that year. Okay, so this is the idea. If I'm compounding annually, this is kind of like that staircase growth that I was talking about. This is, I have $1, and then at the end of the year, all of a sudden I have a new $1, and it just pops out of nowhere. So if I'm doing a compound annually, this is just like one time a year. Maybe I shouldn't put that. We'll say n equals 1. Okay, so when we sub into our formula above, I think this guy's pretty easy to calculate. We have 1 plus 1 to the exponent 1 times 1, so we get $2. Okay? So this is that doubling idea. If I compound once and I'm getting 100% growth, I've got $2 at the end of the year. That's what we should expect. But the more often I compound, my interest will also earn other interest, right? I earn interest on previously earned interest. So if I do semi-annual, my n is 2. And let's calculate here. We should expect to have a little bit more than $2 because I'll compound it and I'll get some interest on my compound from the first time I compounded, once I compound the second time.
So you compound it once and then again.
Right. So it'd be like after 6 months, I compound it, and then after another 6 months, it gets compounded again. So what do we get here? What'd you get, Rachel? 2.25, yeah. Great, okay. So I think we can continue this. So we're gonna need some people out there calculating. Let's continue and see. If I compound 4 times a year, so every 3 months, let's see how much we end up with at the end of our year. 2.44, exactly? Okay. And so on, we'll say. We know we usually round money to like 2 decimal places, but once we get down to the bottom here, I'm going to want a few decimal places. So, okay, monthly, that would be n equals 12. Give me a couple more decimals. 303,529. That's good. Okay, daily, 365. Okay. Secondly, how many seconds in a year? We need to calculate that.
1, 5, 36. The 8.
To the 8?
Yeah.
Oh,
Times 10 is 8.
let's get the actual number.
31 million. 31.5 million.
I want, exactly?
31.536 million.
52 times 6 times 24.
365 times 24 times 60 times
60
60.
times 60. Yeah.
I should be 364 and a half, but
6, 9, 5, 6, 8.
365 is okay.
974, 26.
Okay, we need a consensus on this.
2695.
365 times 24 times 60.
24 times 60 times 60. Oh yeah, 315.
Yeah,
315.
31,536,000.
Yeah.
Exactly?
Yes.
Yes.
Oh, 31,536.
Yeah.
Yeah?
Yeah.
Okay. Okay, there it is. So we're going to sub this in.
Depends on the area.
I don't know.
What?
Good? Who asked me to scroll up? Okay. Get what you need to get. Oh, okay. Yeah, I can do that.
Okay, you get $2.
Okay, what do we get, guys? Let's calculate this.
2.7182.
Keep going, Anil.
8, 2, 8, 1, 6, 1, 5.
Okay? And continuously, so n equals infinity. Of course, we know we can't calculate this. If we calculated maybe a huge number, we could potentially do that. We would want it to be bigger than this. But I don't think we need to calculate this. I will just tell you. It would be equal to, I'm just going to calculate it here so I have all the decimals.
7182818.
Yes, so it's going to be equal to,
That's a big return. $1.7.
and so on.
Ms. McGillis, if you think about it though, like if you're looking at it on even like a secondly scale, isn't the money just like apparent, like it's still just comes out of, like it's not like slowly growing. Like if you look at, like compared to every second, it's still the same like step up, like a staircase.
Yeah,
Like it
but
would be-
eventually, like instead of the staircase being like this, eventually the staircase is going to be like this, and then the staircase will be
Yeah.
like this, right? So it'll
Yeah.
get smaller and smaller and smaller so that it converges toward this like curve, right? So that's
I guess
kind of the idea.
If it's continuous, then yeah.
Yeah. Also, we know, guys, like when we think about exponential growth, if I'm only compounding the interest at the end of the year, I really don't have a curve in between that because my money is actually not growing in between that. So I actually just have a point, and then I have my next point over here, and I don't have any growth happening between those points. But when I do it secondly, I do have growth happening between those points. So I have a curve that's developing from that. Okay, so this is the idea. When I compound continuously, or we have continuous natural growth, I don't keep, like, I'm never going to get from my single dollar that I invest, I'm never going to get like $1 million, even if I compound it tons and tons and tons over a year, right? Eventually it has to converge toward a value, and that value that we converge towards is the value E. Mark?
Like, since it's to the power of infinity,
Okay, guys, too many conversations happening right now. Mark is talking. Go ahead.
since it's to the power of infinity, even if it's growing by an infinitely small amount, wouldn't it just keep growing forever and then wouldn't it go to infinity?
So I think the key is that we have also 1 divided by infinity here, which gives us like an infinitely small number, small decimal.
We're adding infinitely small decimals over and over again. So
We're putting them to an exponent,
Yeah.
right? But if I have, we know 1 to any number is usually just like 1, right? So if I'm adding kind of like infinitely small decimals here, eventually it has to converge towards some value. Because we know, like, when I put exponents on 1, it doesn't change very drastically, right? So here, kind of what we're doing is, here we add 1 to 1, but then we're adding smaller and smaller decimals as we compound more regularly. So here I'm adding 1 to 1, but then I'm adding 0.5 to 1, and then I'm adding 0.25 to 1. And because this exponent is growing, the money is growing, of course, but I'm starting to add smaller and smaller decimals to 1. So what happens is I'm putting exponents, bigger exponents, to smaller values of decimals of 1. So eventually it has to converge toward 1 single value. Zainab? So this is just basically like, this is a number that's been discovered, and it's kind of like when we have continuous natural growth, that happens to be kind of this cool number that all of our stuff is converging toward. So this is just kind of the idea of E. Okay, so E, yes?
Wait, so does that number technically mean that like you can't have any more than that if it converges to that one number?
Yes.
If it's compounding 100%, I think.
Yeah, so we're just talking about growth by 100%, like doubling growth. Okay, so E is irrational like pi. E is approximately equal to a number, and so on. Okay, this number is stored in your calculator. The thought behind E is that it represents continuous natural growth. Okay, that is the thought. So E is already stored in your calculator. You should know where your E button is. And then we know that exponentials are the inverse, or maybe I should say it the other way around, logarithms are the inverse of exponential functions. So if I'm just talking about a regular exponential function, Ryan, are you going to stop talking at any point today? Okay, cool. Thanks. So if I have a regular exponential function with some base b, its inverse, anyone remember what the inverse function of, ooh, not ln, of a regular exponential? Zainab? No? Log, yeah. So it's y equals log base b of x. Okay, so those two functions are inverses of one another. When I hone in more specifically on the exponential function e to the x, okay, it is, the inverse of this is technically y equals log base e of x, similar to how when I have just a general base b, it's log base b of x. But we have a special logarithm for this because e is a special number, and a log to base e is actually ln. Okay, so that's kind of where that comes from. So e to the x and ln of x, those two functions are inverses of one another. Okay, some other little notes that you may want to remember is that if I have the ln of e, when we talk about logarithms, logarithms are asking the question, what the base of that logarithm to what exponent gives me this value right here. So if the imaginary base of a ln is e, I'm really asking myself e to what exponent gives me back e. So what is the answer to this logarithm? E to what exponent gives me e? 1. So the ln of e is actually equal to 1. Okay? Because the base of that logarithm is e. So if you ever see the ln of e in your travels, you can replace it with 1. Okay? This is similar to, if that is confusing to you, if I had something like y equals log base 2 of 2, it's the same kind of idea. So what I'm asking myself in this scenario is this base 2 to what exponent gives 2 back? Well, 2 to the exponent 1 gives us 2 back. So the answer to this logarithm is 1. Okay, so that's kind of the same idea. Because ln is actually a logarithm with base e, it's like log base e of e. Okay, we don't ever really, like, I shouldn't really write this here. We don't really write that there, but just so you guys know that the base of that is e. I wrote it this one time. Okay? Okay, so we have some graphs of e and ln, just to remind you kind of what these functions look like. So in advanced functions, we talked about kind of like 3 key pieces of information that we use to graph exponentials and logarithms. That's really all you need to create a general sketch. Of course, you can always choose a few more if you want. If you wanted to do -2 to +2 and sub them into your equation and get your y's, you can do that. But we need the 0 point, we need the 1 point, and any basic exponential function like this, some base to the exponent x, will have a horizontal asymptote resting on the x-axis, or y equals 0. Okay, and then I just get my y's. So these are my 3 key pieces of information. I get my y's by subbing the x's into e at x, e to the x. So e to the exponent 0, anything to the exponent 0 is 1, and e to the exponent 1 is e, which we know to be about 2.72. So when I graph it, I'll graph it around, I have to approximate it around 2.72. And because ln is the inverse of e, I just talked about this with my grade 11 class actually. All I need to do in order to find the points of an inverse function is swap the x's and y's. So I literally take 0, 1 and it becomes 1, 0. And I take 1e and it becomes e1. Anyone remember what horizontal asymptote becomes? Yeah, vertical asymptote at x equals 0. Good. Okay, so we'll just sketch these guys out quickly here. So I'm sketching the ln of x right now. Okay, so there's our two graphs. Also, if you guys just remember back from grade 11 when we were doing inverse functions, our inverses are reflected over the diagonal line y equals x. So these two functions, because they're inverses of one another, if you imagine kind of folding your paper over that dotted line, it should look like these guys match up. Okay, I can also do this technique of graphing with any basic exponential function. It would just be find the 0 point, find the 1 point, and it has a resting horizontal asymptote at y equals 0. So whatever the base is, it just changes based on how your base of your exponential function changes. And then the base of your logarithm, that's what changes as the base of your logarithm changes. So here, when I have ln x, the base is e, so I have the point e1. If I had the log base 2 of x, I would have the point 2,1. Or log base 3 of x, I'll have the point 3,1, and so on. The other points, the 0, 1, and the 1, 0, for each of those, that is the same for all of them, unless I have transformations happening, and then, of course, those points shift. But for the basic exponential and logarithm, that's kind of the three key pieces that you need. Good. Does everyone have their graphs down? Oh, thank you. Yes. I wrote x equals 0 accidentally.
Oh, on the y-axis.
Axis.
Sure, on the x-axis.
No axis.
Alright.
Okay, so we're gonna just refresh our memory on some log rules here. Okay, today's lesson is just kind of review of our logarithms knowledge. So when I see e in a question or ln in a question, I want to think about using like ln and e. If I'm working with other exponentials, I use log rather than ln. Okay, so anytime I'm trying to isolate for an exponent, I want to get the base and the exponent alone on one side. So my first step here would be to divide out this 100. Okay, and then if I have an unknown in my exponent, I am going to, usually we would log both sides, but because the base of this is e, we use ln. So we're going to ln both sides, and I get to use that parachute rule that we talked about in advanced functions, where we parachute that exponent down in front as a multiple. Okay, and there's that lovely ln of e that we talked about earlier. What is the ln of e equal to? 1. Okay, so because that equals 1, we have ln 5 equals the ln of 2x. Okay, so here's my question. The ln of 5, is the ln of 5 equal to anything other than the ln of 5? Okay. What? No, your answer should be no. The ln of 5 is only going to be equal to the ln of 5. So what do I know about 2x? 2x must be equal to 5. Good. So I'm not canceling the lns here. I'm just using a little step in my common sense and logic that says that if I have the ln of something equals the ln of something else, the first something must be equal to the second something, right? 5 must be equal to 2x if this statement has to be equal, right? Because the ln of 5 is not going to be equal to anything other than the ln of 5. So 2x has to be equal to 5. Does that make sense? Okay, so our x value here is 5 over 2. How do I check my answer for these again? We plug it right back in, make sure we get left side equals right side, okay? Okay, if you leave your answer in fraction form, you won't have to worry about any decimal rounding or anything like that. I know this one is a finite decimal anyways, it's just 2.5, so you could enter it in as 2.5, but if it were something like 5/3, which is a repeating decimal, I would probably want to enter it into my equation as 5/3, and then I can know for sure whether it's equal to 500 or not. Sweet. Questions on that guy? Okay. So the distinction between, sometimes we can get confused because ln doesn't look like log, but I want you guys to think about ln as if it's a logarithm, right? It's just a logarithm with base e, we just write it a little bit differently. So I should be able to use any of my log rules with ln, right? Just like we use this like parachute rule up here with my ln, I should be able to use the sums rule here with these ln expressions. So sums become products. Okay, so in the logarithm, so this will be the ln of 2x. Okay, so sums become products. And then something that we learned about in grade 12 was inverse form, switching between logarithmic form and exponential form. So we want to imagine this as the base of e. So when I go to use inverse form, I do e. The answer to the logarithm is the exponent. Okay, so this is our base, and this is our exponent. So e to the 3 equals 2x. That's how we're going to solve that, because we can't really get that 2x outside of the ln any other way than switching. So this is what we call inverse form, right? We switch between that exponential and logarithmic form. And then I'm just going to divide out the 2. And we will get e to the 3 over 2. We'll just leave it like that. Okay, and again, I should be able to just sub this right back in for x here and check that the ln of 2 plus the ln of e cubed over 2 equals 3. Okay? Any questions for that one? Okay. And then we're just going to do an application question just to remind us about how we do these. So we have a bacteria culture, and it's given as a function of time by the equation p at t equals 200 e to the exponent 0.094 t, where p is the population after t days. What is the initial population of the bacteria culture? So how much time has passed when I take the initial sample and I figure out the initial population? 0 time. So A, initial time, means time is 0, right? So all I need to do is evaluate P at 0. Okay, and what this should usually give you when you're working with exponential functions, if you have no transformations or anything like that, this whole thing becomes 0, and e to the exponent 0 is 1. So we get 200 times 1. So that should give me my initial population of 200 cells, we'll say. Okay, so that one is just subbing in and calculating. Estimate population after 3 days. I think we should be able to do this. Grade 9s could do this one too. We're evaluating P at 3. And we'll probably have to round this one a little bit, so I'll just do the approximation symbol there. What'd you guys get?
265.15.
Hayden, did you get the same thing?
0.1557.
557, okay.
Yeah.
Yeah, okay. So I think we could probably say like approximately 265 cells, because usually we don't have, I guess if the cell is growing, then we have 0.15, but maybe we'll just say approximately 265.2 cells. Okay. How long will the bacteria culture take to double its population? Okay, so this is kind of more of a solving involving logarithms type thing, because we'll have to solve for the time, which is in the exponent here. Stretch or questions? Okay. So my initial population is 200. I should set my p at t equal to 400 here if I want to figure out how long it takes to double. I want to know when 200 is going to become 400. Okay, just as I showed you above, before I do any ln or anything like that, I want to make sure that I have the base and the exponent isolated on one side. So I'm going to divide out that 200. And then, now that I have the base and the exponent isolated, I can, technically guys here, you can use log. It just is easier when we use ln, because we'll always end up getting like a ln of e, which we can just set equal to 1. So it's nice to use ln when you have a base of e for that reason. And we can bring our exponent down in front, parachute rule. Okay, and this is kind of what I was just talking about. So we have this ln of e, which we know is equal to 1. So now we know that we have ln of 2 equals 0.094t. And I just have to divide out the 9.4, or 0.094. Okay, and we'll just calculate this one, because it's actually asking for time, so it might be nice to have like a rough time estimate here. Mark?
Isn't that the same as doing inverse form?
Like at what step here?
Oh, when we put ln on both sides?
Mm-hmm. Yeah, you can switch between forms. What did we get here? Sorry, was that 7.37, did you say? 37. Okay, that's good. So approximately, what are we measuring time in here?
Days.
Okay, so approximately 7.37 days. Okay, the last part of this asks me to rewrite this function as an exponential function with base 2. So I know the doubling period. When I write something with a base of 2, I'm talking about the doubling time, right? So essentially it's asking me to kind of fill in the blanks here. So it's asking me if I have a base 2, how do I fill in this exponent? We still have an initial population of 200 cells. And then I need to fill in this exponent. So usually this exponent here is total time over the doubling period. So how long does our population take to double? Okay, so that's my doubling period, right? So it's about 7.37. We can use 39 there. Okay, and if you want, you can do a little test with 3, because we calculated 3 days earlier. So if I sub in t as 3, I should get the same population out to 265.15, whatever, if we've done it correctly. So we'll just double check our work. 3 as that exponent there. Yep, gives us 265.1558 and so on. Okay, it might be slightly off the decimal just because of our rounding with this decimal here. So if you want it to be exact, you can actually put it as the ln of 2 over 0.09, which maybe we should do. Ooh, my eraser works now. So maybe we put it as this just to be more precise. And then I could make you flip and multiply and all that good stuff, but we'll leave it there. Sarah?
Can you explain how you made the equation again?
So initial population doesn't change, right? So this is my initial population. They want us to express it as a doubling equation, so base of 2.
Oh, okay.
And then capital D, this is total time. So that's always changing, right, depending on what we're calculating. Little d right here is the doubling period, which we just found in part C.
Okay. Thank you.
Yep. Does that make sense?
Yeah.
Okay. Cool. Okay. I think that's it, right? Okay, so you guys can do a sampling of these questions. I don't think this is a lot, so I don't know if there's like multiple questions within questions here. Let me just see. 265.